Why was quantum superposition so hard for early physicists? Imagine trying to picture a tiny particle that can be in two places at once. Sounds strange, right? That's what quantum superposition is all about. Early physicists found it tough to accept because it went against everything they believed about how objects behave. Before quantum mechanics, scientists thought objects had definite states. A ball was either here or there, not both at the same time. But in the quantum world, particles like electrons or photons can exist in multiple states until someone observes them. This idea was so different from everyday experience that it was hard to understand. One big challenge was visualizing superposition. Think of Schrödinger's cat, a famous thought experiment. It imagines a cat that is both alive and dead until someone opens the box and looks inside. This paradox shows how strange superposition feels when applied to real objects. For tiny particles, it's easier to accept because they behave differently from big objects. But imagining a cat or a person in multiple states at once is much harder. Another problem was the math behind superposition. Quantum mechanics uses wavefunction to describe particles. These wavefunctions tell us the probabilities of finding a particle in certain places or states. But translating these probabilities into a physical picture was confusing. Early scientists struggled to understand what the wavefunction really meant. Was it a real thing or just a way to predict outcomes? This question led to many debates. The measurement problem added to the confusion. When a measurement happens, the superposition seems to suddenly collapse into one state. But why does this happen? How does the act of observing change the system? Early physicists debated whether the wave function was a real physical object or just a tool for calculations. This uncertainty made superposition even harder to accept. Many scientists were trained in classical physics, which sees the world as predictable and objective. Quantum ideas challenged that view completely. Einstein, for example, thought quantum mechanics might be incomplete because it implied spooky action at a distance and particles being in multiple states at once. Finally, experimental evidence took time to gather. Early experiments like the double-slit experiment showed interference patterns that hinted at superposition. But understanding what that meant took decades. It was only after more precise experiments confirmed superposition as a fundamental principle that physicists started to accept it fully. Understanding superposition is key for modern quantum technology. It allows quantum computers to process many possibilities at once, making them much more powerful than traditional computers. Visualizing superposition involves thinking of quantum states as combinations of basic states, where the system holds information about all these states until measured. This idea is at the core of quantum cryptography and sensors. In the end, superposition was so hard for early physicists because it went against their classical intuition. It introduced strange, probabilistic, and non-local phenomena that challenged their understanding of reality. Over time, with better math and experiments, it became a fundamental part of quantum mechanics and the foundation for new technologies.